This is the fifth and final section of chapter 7 on the simplex algorithm, and this is the big M method. So first of all, M stands for or represents a very big or arbitrarily large number, and that gives this method its name, hence the name big M. Now, in the two-stage or two-phase simplex method, our aim in the first stage was to minimize a new objective or temporary objective function I, which was the sum of the artificial variables, i.e. what we wanted to do was to make the sum of the artificial variables equal to 0. And now, since the artificial variables are all positive, it meant that all of the artificial variables are equal to 0. Now, by using M, big M, we can reduce this two-stage method to a single one-stage method. So how is that possible? What do we need to do? Well, let's take an example. Let's say that our objective function was to maximize this p equals 3x minus 2y. What we can do so that we're able to minimize our artificial variables, we can write the original objective function minus m times the sum of our artificial variables. Now, the maximum of p will occur when this bit at the end is 0. So we've got that statement here, when m times the sum of our artificial variables equals 0. Now, since m is a very large number, its whole value of this expression here is only going to be equal to 0 when the sum of the artificial variables equals 0. So you can see that this achieves the same as the first stage in the two-stage simplex method. So the only thing that's really going to change when we use this method is that when we have a maximization problem, we'll subtract m times the sum of our arbitrary, our artificial constants, artificial variables, and when we minimize p, it will be adding m times the sum of our artificial variables. So that means that when we do our table using the simplex method, what we will have m's on the bottom row, but we just treat these as large numbers and we proceed exactly the same as before. Example 17, we want to solve the following linear programming problem using the big M method. We want to maximize this objective function subject to these constraints. So the first thing we're going to do is to turn these inequalities into equations less than or equal to, so we add a slack variable, x minus 2y minus z, again less than or equal to, so we add another slack variable. Third one is greater than or equal to, so we subtract a surplus variable, add an artificial variable, make that equal to 4. Let's look at the objective function, and that's to maximize p equals x minus y plus z. Now, since it's maximizing, we need to subtract big M multiplied by the sum of the artificial variables, which is just a1. So when it's maximizing, we subtract. If it was minimizing, we would add. Okay, so now we're going to do some substitution. So we want to work out what a1 is. We can do that from the third equation there. So we have 4 minus x plus s3. So p now becomes x minus y plus z minus m times by 4 minus x plus s3. We want to expand the brackets and simplify it and collect together any like terms. Now when I expand this bracket here, I'll end up with a plus xm, and I've already got an x term here, so they can go together. I've already got an x plus xm or mx. There's only a single y, a single z, then multiplying out the rest of the brackets, I have minus 4m minus m s3 or s3m. So I now have everything I need to go into my Tableau. So those, oh, and that needs rearranging before we put it into the Tableau. So that'd be p minus 1 plus mx plus y minus z. Now, this is a number. So this is going to go the other side of the equal sign. It's going to stay on the right hand side. So plus m s3 equals negative 4m. So remember, this here, anything with m and a number is just a number. Negative 4 times by a very big number. Now we're ready for the Tableau. So we've got x, y, z, s1, s2, s3, a1, p, whatever the value of the equation is, and we'll do our working in that last column. So we've got 2x plus y plus z plus s1 is equal to 20. That's equation number 1. Equation number 2 is x minus 2y minus z plus s2 equals 7. And the third equation is x minus s3 plus a equals 4. Then we'll look at our objective function here. So we have p, and then the coefficient of x is minus 1 plus m, plus y minus z. The coefficient of s3 is m, no a, and its value is negative 4m. Right, so we need to find the pivot column first of all. So the pivot column is going to be the most negative value, and that's this column here. So let's fill in the theta column. So 20 divided by 2, 7 divided by 1, 4 divided by 1, it's 4. So we have this as our pivot row. So the pivot value is 1, which means that this row here is going to remain unchanged. That can go straight into the second Tableau. So we'll put our headings in like this, and row 3 will go straight in as 1 0 0 0 0 negative 1 1 0 4. Then to get our new row 1, we are going to take row 1 and take away 2 lots of row 3. To get our new row 2, we're just going to take away row 3, so row 2 minus row 3. So these are row operations. And then for the bottom row, row 4, we need to add, because we've got a minus here, add 1 plus m lots, the coefficient lots of R3. So then let's now fill that in. So the top row now becomes 0, 1, 1, 1, 0, 2, negative 2, negative 2, 0, and 12. Row 2 now becomes 0, negative 2, negative 1, 0, 1, 1, negative 1, 0, and 3. And then the bottom row becomes 0, 1, negative 1, 0, 0, negative 1, 1 plus m, 1, and 4. Now I just want to talk through how we get the results for a couple of these. So we're going to start with this one here. So the old row 4 was m, and we're adding m 1 plus m lots of the pivot row value, which is negative 1. So this basically becomes m minus 1 minus m. So you can see that it just becomes negative 1. We're going to do the same thing with this, sorry, not that one, this one here. We're going to work out how we ended up with 4 there. So The old value for row 4 was negative 4m, and we're adding 1 plus m lots of row 3, and row 3 is 4. So basically what this becomes is negative 4m plus 4 plus 4m. So you can see it just becomes 4 in that cell there. Right, now I pick my pivot column. Now there are two negative ones. I could pick either one as the pivot column. I'm going to pick this one, the Z column, simply because it's just the first one that I get to. So there's my pivot column there. Let's do my calculations. 12 divided by 1, 3 divided by negative 1, which is negative, 4 divided by 0, well that's infinite. So that means that my pivot row is the top row. So we'll just highlight that there. So my pivot value now is 1, which means this top row remains unchanged. So let's just put in the column headings, and then we can copy straight down our row 1, because basically what we're doing is dividing that row by 1 effectively. Right, so we will have 0, 1, 1, 1, 0, 2, negative 2, 0, 12. So this is our new row 1. So just mark it down as row 1. So we want to get this as 0. So row 2, we're going to add row 1. Simple enough. Okay, right, row 3 is already a 0 there, so that's unchanged. And then negative 1, we want to add a row 1. So row 4 will add row 1. So once we've carried out those operations, this is what the table will become. So row 2 becomes 0, negative 1, 0, 1, 1, 3, negative 3, 0, 15. Row 2 becomes 1, 0, 0, 0, 0. So remember this is unchanged. 1, 0, 4, and then the bottom row becomes 0, 2, 0, 1, 0, 1, negative 1 plus m, 1 and 16. Okay, so let's just talk about how we got this one here. So the old row 4 was 1 plus m. Then we're adding row 1, so we're adding negative 2 to this, or taking away 2. So that's why it becomes negative 1 plus m. Now you'll notice there are no negatives in the bottom row. That's a very big number, -1, so it's still positive. So we found an optimal solution. So we'll just write down, since there are no negatives in the bottom row, we have an optimal solution. So what is our optimal solution? Well, let's read off. So the x column has a 1, so the value of x is 4. Right, y column, okay, there's not a single one, so the value of y is 0. How about z? Z column, there's a single one, z is 12. Okay, how about s1? S1 and actually s2 and a1 are all going to be 0. And the only other one that has a value will be s2. S2 is 15. So I'll write that down. S2 is 15. And then S1 and S3 and A1 are all equal to 0. Now, it's probably worth at this point just checking. There's so many little calculations to do, it's useful to check whether this is optimal or not. So let's put these values into the equation. So if I put these values into the first equation, I'll get 2 times x, which is 8, plus y, which is 0, plus z, which is 12, minus s1, which is 0, so we get 20. Okay, so that's correct. So if I look at the second one, so x, which is 4, minus 2y, so that's 0, minus z, so we're minus 12, plus S2, so plus 15, and that equals 7, so that's correct. Then the last one, we will have 4 minus 0 plus 0 is 4, so that also is correct. It satisfies all the equations, so that's useful. Now before we move on, just a quick note about when we picked the pivot columns, we had a choice. So if we went back here, we picked this as a pivot column. Now if we had picked this as a pivot column, it would have taken us twice as long to find an optimal solution. In fact, we would have had 6 tableaus before we found a solution. Now, one way of quickly checking is just to quickly check which one is going to give you negatives in the bottom row. A quick check of this shows you no negatives in the bottom row, whereas this, we'd still have 2 negatives in the bottom row if we chose that. But as I said, I picked that, we got to the solution much more quickly. Example 18, use the big M method to solve this linear programming problem, and you'll notice here it says minimize. So let's start with the equations. So we will have 2x plus y, 2x plus y plus z is less than or equal to, so we add a slack variable. Second one, x minus 2y minus z is less than or equal to, so we add a slack variable. It says x is greater than 4, so we subtract a surplus variable, add an artificial variable, and make that equal to 4. And actually, the only difference between this and the previous example is that it says minimize. So if we're going to minimize p equals x minus y plus z, remember we need to add m times the sum of the artificial variables, but we need to multiply it by -1, so it becomes maximizing negative p equals x minus y plus z plus m times a1, which becomes maximizing p equals negative x plus y minus z minus m times by a1. So let's work out what a1 is using the third equation there. So a1 is equal to 4 minus x plus s3. We'll substitute this here. So the objective function now becomes p equals negative x plus y minus z minus m times by 4 minus x plus s3. Like previously, we want to see if there are any like terms we can collect. Yes, there are, because here we're going to get plus mx. So we will have, in terms of x, a -1 plus an mx, a single y, a single z, and then minus 4m, and then minus ms3. So what we'll now have is p minus -1 plus mx minus y plus z plus ms3, big S there, not a little s, equals -4m. Now when we put the coefficients in the table, this bit here, basically, if you've got -1, so this is basically just going to become 1 minus m. So when I put it in the table, I'll just put 1 minus m there, because that's what this becomes. Okay, so our initial tableau, if we look at equations, 2x plus y plus z plus s1 equals 20. Second equation, x minus 2y minus z plus s2 is equal to 7. Third equation, x and then minus s3 plus a1 is equal to 4. Then our objective function here, we've got p, and then the coefficient of x is 1 minus m, and then we've got -y plus z, no S1 or S2, we've got m of the coefficient of S3, no A1, and its value is negative 4m. Right, so our most negative value is going to be this one here, because it's effectively negative m plus 1. So let's highlight our pivot column. So to find a pivot row, we will now do 20 divided by 2, 7 divided by 1, 4 divided by 1. So this is our pivot row. That's going to remain unchanged. So we'll put our headings in, and we can copy that row directly into our tableau, and that is row 3. So we will have 1 0 0 0 0 negative 1 1 0 4. So this is our new row 3. So what are we going to do? We want to take 2 lots of this away from row 1. So row 1 minus 2 lots of row 3. The other row operation, we're just going to take away row 3 from row 2. So row 2 minus row 3. And then for row 4, we want to subtract 1 minus m lots of row 3. So here, row 4 minus 1 minus m lots, 1 minus m, of row 3. So we'll fill those values in. So the top row will become 0, 1, 1, 1, 0, 2, negative 2, 0, 12. Row 2, 0, negative 2, negative 1, 0, 1, 1, negative 1, 0, 3, and bottom row becomes 0, negative 1, 1, 0, 0, 1, m minus 1, 1, and negative 4. Right, so let's have a look for our pivot column, which is going to be this one here, because we've got the negative 1, that's the most negative value. Remember, this is a very big number, minus 1, so it's still positive. So let's work out our theta value. So 12 divided by 1, 3 divided by negative 2, it's negative, so we don't bother about that. 4 divided by 0, that's infinite. So that gives me the top row here. So my pivot value is 1, which means that row is going to become unchanged. So let's just copy that in. 0, 1, 1, 1, 0, 2, negative 2, 0, 12. So this is our new row 1. What we're going to do to row 2, well, we're going to add 2 lots of row 1. So row 2, add 2 lots of row 1. Row 3, there's already a 0 there, so it's unchanged. And then in row 4, we're just going to add row 1. So row 4 plus row 1. So now we'll complete the rest of the table. So row 2 becomes 0, 0, 1, 2, 1, 5, negative 5, 0, 27, 27 or 29. Row 3 becomes 1, 0, 0, 0, 0. So this is unchanged. So I'll just write that down, it doesn't become anything. And the bottom row becomes 0, 0, 2, 1, 0, 3, m minus 3, 1, and 8. Now you can see there are no negatives in the bottom row. That's going to be positive. So we found an optimal solution. Right, so let's write down this optimal solution. So x is 4. X equals 4. Then we have y is 12. Y equals 12. Okay. Z S1 R0. S2 is 27. So S2 is 27. So we know that Z, as we said, S1 S3 and A1 are all 0, and the value we've got for P, if we read it off, is 8. Right, so just like the previous example, what we're going to do is we are going to just quick check to see if these values satisfy the equations that we had before. Right, so what were they? So 2x, that's 8, plus y, which is 12, plus z, which is 0, plus s1, which is 0, should give me 20, so it does. Second equation, x, which is 4, minus 2y, so that's minus 24, 2 times 12, minus z, which is 0, plus s2, which is 27. That does give me 7, so that's correct. 4 minus 24 is negative 20, plus 27 is going to be 7. And then the last one, x, which is 4, minus s3, which is 0, and a1, which is 0, gives me 4. So that's just a check that shows me that those solutions, optimal solutions, satisfy those equations. Example 19, set up the initial tableau for solving the following linear problem using the big M method. So you want to maximize this subject to these constraints. So the first thing that we need to do is to change our inequalities into equations. Less than or equal to slack variable. Second one, greater than or equal to surplus variable. And artificial variable, which should be equal to 10. Third one, greater than or equal to surplus variable, artificial variable. Then we want to maximize P equal to 3x minus 2y plus z minus m times the sum of our artificial variables. That's a1 plus a2. So a bit of algebra to do here. So a1 from the second equation is 5 minus 2x plus 3y minus z plus s2, and a2 is equal to 8 minus x minus y plus s3. So a1 plus a2 is going to be 13 minus 3x plus 2y minus z plus s2 plus s3. Now all of that, this bit here, needs to go in this bracket and get multiplied by m. So it'll probably be easier to do it as we go along rather than write it down then multiply it out. So we've got 3x minus 2y plus z. Right, so let's multiply each one of these by negative m. So, and then we'll collect the terms. So minus 13m plus 3mx minus 2my plus mz minus ms2 minus ms3. So now we'll collect the like terms. So we've got 3x and 3mx. So we'll write that as 3 plus 3mx. So that's our x terms. Now y terms, we've got negative 2y and negative 2my. So we'll write that as negative and then 2 plus 2my. Then we've got z plus mz, so plus 1 plus mz. Then we've got other terms we can't collect, so we've got minus 13m. Then it looks like we've got minus ms2 and minus ms3. Now remember, we need to write this equal to a number. Remember, this minus 13n is our number. So we now get maximizing p minus 3 plus 3mx plus 2 plus 2my minus 1 plus mz plus ms2 plus ms3 equals negative 13m. So now we can put the coefficients into our tableau. So we have x plus y plus 2z plus s1 is equal to 10. Second equation, 2x minus 3y plus z minus s2 plus a1 is equal to 5. And third equation, x plus y minus s3 plus a2 is equal to 8. And then we have our objective function. So it might be a bit squashed to get these in the boxes. So we've got p, and then coefficient of x is negative 3 minus 3m. So let's write it like this, minus 3 minus 3m. Then for y, it's 2 plus 2m. Then z, it's going to be negative 1 minus m. For S1, it's going to be 0. S2 and S3 are both m. And its value is negative 13m. So the very first column is where I find the most negative values. And then we'll do theta, so 10 divided by 1, 5 divided by 2, 8 divided by 1. So we can see that our second row is going to be our pivot row. So 2 is the pivot value, which means what I need to do is to take this row, row 2, and divide it by 2. So this is what my row 2 is going to become. 1 minus 3 over 2, a half, 0, negative a half, 0, a half, 0, 0, 5 over 2. So this is my new row 2. Okay, how am I going to get 0 in this box here? I'm going to take my row 1 and minus row 2, and I'm going to do the same in row 3. Row 3, I take away row 2. And then in the bottom row, I need to add basically this lot of row 2. So row 4 plus negative 3 minus 3m lots of row 2. Actually, that should be minus, shouldn't it? Which is basically the same as saying row 4 plus 3m, or 3 plus 3m. So let's fill in the tableau now. So row 1 becomes 0, 5 over 2, 3 over 2, 1, a half, 0, negative a half, 0, 0, 15 over 2. Row 3 becomes 0, 5 over 2, negative a half, 0, 1 half, negative 1, negative a half, 1, 0, and 11 over 2. And our objective row at the bottom becomes 0. There's going to be a bit of a squeeze here. Negative 5 over 2 minus 5 over 2m. Then we have half plus half m. Then 0. Then we're going to have negative 3 over 2 minus a half m. Then m. Should have made these boxes bigger really. 3 over 2 plus 3 over 2m, 0, 1, and then 15 over 2 minus 11 over 2m. Right, now this actually sets us up now to answer this question because we don't need to answer it fully. So the initial tableau is here. So here's my answer to part A. Part B says find the value of the first pivot. Well, our first pivot was 2, so we'll put B. Actually, let's do it up here. We've got a bit of space. So B, the value was 2. Part C, carry out one iteration to state the value of each variable at the point. We've carried out the first iteration here, so we can now state the value of each of the variables. Okay, so reading off from the table, there's only 3 of the variables have a non-zero value. That's x, s, and a2. Everything else is 0. So x, reading off from the table, is 5 over 2. X is 5 over 2. The other one that has a non-zero variable is S1. S1 is 15 over 2. And the other non-zero one is A2, which is 11 over 2. So everything else, so Y, Z, S2, S3, and A1 are all 0. And then the last part, part D, asks us explain why the solution given by the first iteration is not feasible. Now remember, the whole point of this big M method is to make the value of the artificial variables equal to 0. Now we've got the value of one artificial variable as 11 over 2. So this is not a feasible solution. So we can say the solution is not feasible since we have an artificial variable a2 is not equal to 0. You should now be able to do exercise 7E on pages 211 to 212 and then go on and complete the mixed exercise for chapter 7.